Okay, let's get started. Thanks for coming to today's Microsoft Research AI Distinguished Lecture. It's an honor today to have Michael Kearns with us. Michael is professor and the National Center Chair in the Computer and Information Science Department at the University of Pennsylvania. He also has appointments in the Economics Department and at the Wharton School of Business. He's the founding director of Penn's Warren Center for Network and Data Sciences. He's, as you all know, published widely in machine learning, algorithmic game theory, and quantitative finance. He's, beyond his scholarship, he's worked in the finance and technology industries. He's consulted for government agencies and companies on legal and regulatory matters involving algorithms, data, and machine learning. He co-authored an introduction to computational learning theory. And beyond all that, as I mentioned, we had a great session last night at Seattle Town Hall with Aaron Roth, his co-author on the ethical algorithm. And as I mentioned last night to the audience, I have a really distinct memory of first meeting Michael at UAI 1986 in Philadelphia. He was right over here at the side of the room, and I looked over, and he was giving a presentation. I was very impressed with his crispness, and I thought to him, because we had the old timers, the founders of the UAI conference from 1985, that was the first one. We were all there, and I was like, who is this new person who is saying all these interesting things? And I followed his work ever since. And he and Aaron Roth wrote this, I think fabulous book. I had to read it because I moderated the session at Seattle Town Hall last night. And I was really happy to have forced myself to read every page of it, and really, really enjoyed it. It's a really fabulous contribution to the discussion on the role of algorithms and the rising interest in their influence, inadvertent and even malicious, in the world. And the fact that the book goes from some of the topics we all know and study, fairness and bias and intelligibility and explanation and privacy issues, that many topics we cover at Microsoft Research and on the Ether Committee efforts at Microsoft, also dives into science, which I thought was my favorite chapter on, sort of how the inferences we make in our scientific endeavors are a great bulk of these inferences and results are likely to be non-reproducible and false. With that, Michael.
Okay, great. Okay, thanks, Eric, for the kind introduction and for your terrific moderating last night. It was a great event. And it's great to be here. Actually, somehow in my now long career, I've never managed to make it to MSR Redmond, so this is kind of a bucket list visit for me. I'm happy to be here.
You spent time as visiting researcher in Cambridge.
In Cambridge, I've spent time in Cambridge. I've spent a lot of time in the New York lab. I've visited the New England lab, but I've never actually been to the mothership. So.
You were on our tab.
Yeah, I was. My close friend and colleague at Penn, Aaron Roth, and I decided a couple of years ago to write a general audience book. And I'm going to do something a little unusual with this talk because I get the feeling that on the one hand it's a diverse audience, but on the other hand there are probably some card-carrying AI, ML researchers in the room. And so what I want to do is spend the first half of my time kind of giving the description of the book that we give to rather general audiences at the risk of boring the more technical people in the room. But I'm kind of hoping that even if I'm treading over territory that you know well scientifically, or at least familiar with in theme, you might find it interesting just the way that we try to phrase it for a more general audience and get something out of it for that reason. And for those of you that haven't seen these topics, I'm hoping it'll just be interesting outright. But then what I want to do is spend time at the end doing a more deep dive on recent algorithmic work that we and others have been doing on more refined notions of fairness in machine learning and related areas. So our book is called The Ethical Algorithm, this with the subtitle, The Science of Socially Aware Algorithm Design. It just came out officially a couple of weeks ago, although it's been shipping from Amazon for a little bit longer than that. And so what is this book about? So, quickly on the heels of the rush of excitement around the great empirical successes of AI and machine learning in the earlier part of this decade, quickly came like the buzzkill of reports about all kinds of what we might call antisocial behavior by algorithms. Often, but not always, algorithms that really we might more accurately refer to as models, because they are the output of an algorithm that took data that it trained a model on, and then the thing that's actually deployed and making the decisions is, let's say, a neural network, for example. And it's an interesting time to work in the so-called FATE area, fairness, accountability, transparency, and ethics, because literally, I'm giving variants of this talk, all the time these days, and pretty much every single time I'm able to include a fresh mainstream media news report on antisocial behavior by algorithms. I'll mention this week's favorites a little bit later in the talk. But this has been kind of in the public consciousness enough for long enough now that there are some good general audience books that precede us on these topics. You've probably heard or read some of these, like Weapons of Mass Destruction, Algorithms of Oppression. These are really about kind of bias and unfairness in algorithmic decision making, and books like Data and Goliath, which are kind of examining privacy and security issues and making the argument that we have essentially arrived at something akin to a surveillance state. And Aaron and I, as I think many people in this room, doing technical work in these areas, we like these books, and feel like they do an excellent job of identifying real problems and making them kind of visceral to ordinary readers. And so we admire these books and consider them inspirations. But we were disappointed in these books when they came to the parts about what to do about these problems, what the solutions might be. And all these books have sections like that, usually a little bit towards the end. And I perhaps unfairly paraphrase, but I think they're kind of the form like, well, we need better laws, we need better regulations and policies, we need watchdog groups, we really need to keep an eye on this stuff. And Aaron and I agree firmly with all of that. But the part that we were disappointed with is the fact that, as researchers in the field know, if there are problems with algorithmic misbehavior, you could also contemplate making the algorithms better in the first place. Fixing the algorithms in some sense so that they don't entail violations of privacy or racial or gender discrimination and the like. And to be fair, some of these books I think were written when that research agenda was still rather immature, and we don't know as much as we do now. But our goal in writing our book was to kind of tell the world that there is a science. You can make scientific a lot of these questions. Or a lot of these problems of unfairness, privacy violations, interpretability, et cetera, and design algorithms that are demonstrably better in the first place. And so our book is kind of a survey about why you would want to do that, how things go wrong in the first place, what the potential algorithmic solutions are, and also what the costs of those algorithmic solutions will be, because there will be costs to them, as we'll discuss. In an early draft that was sent around for comments and input from various people by our publisher, we got a very interesting critique back, in which the critic basically said, your title kind of is a conundrum or doesn't make sense. Why would you talk about ethical algorithms? Because you wouldn't talk about ethical hammers, for instance. So the point that this reviewer was making is that, look, a hammer is a tool. It is a human artifact designed for a specific purpose. And even though, of course, that tool can be misused, perhaps in unethical ways, I could hit you on the hand with a hammer, nobody would sort of think to ascribe that moral lapse or ethical failing to the hammer itself. They would blame me for hitting you on the hand with it. And so this critic's argument was, algorithms are the same way. You shouldn't talk about algorithms being ethical or not, and you shouldn't talk about like the moral failings of algorithms. You should talk about the moral failings of the designers of algorithms. And we thought carefully about this comment, and we disagree. we think that algorithms, even though they are also tools and artifacts designed for particular purposes, there's a number of things that give algorithms kind of a different ethical or moral stature than their designers, okay? And we go into more detail on this in the book, but the basic argument that we make is, look, especially in the era of machine learning, it can be hard to assign blame to the designer of an algorithm due to the multiple steps involved in the machine learning pipeline and the sort of levels of indirection involved. So, that pipeline usually starts with data gathered from somewhere. And you may not know exactly how that data was gathered or exactly what every attribute means. And furthermore, that data might be a hybrid of multiple data sources whose provenance is sort of uncertain to you. So already from the beginning, the input to your algorithm might be of uncertain origins, and you might not know, for instance, if it's police data, whether the arresting officers might have been racially biased in the first place, and so the data that you see from the beginning has that encoded into it. We then usually use this data to define some sort of objective function or landscape, and primarily that objective function will primarily be concerned with predictive accuracy, for example, and as well say this is one of the problems. Then, of course, we take that data and that objective function and use some complicated optimization procedure like stochastic gradient descent on a multi-layer neural network, and we get some rather complicated looking model. And the point is that after all these steps are done, not only can it be hard, if the algorithm causes harm to some specific individual, not only can it be difficult to sort of say that the algorithm designer was specifically responsible for that particular misdeed. Unlike when I hit you on the hand with a hammer, we may not even know that these harms are being caused until we decide to look at them. So if I hit you on the hand with a hammer, both of us know what has happened, and it's very clear that a harm has been caused to you. In algorithmic decision making, often the harms are subtle, diffuse, and until somebody bothers to look and document them, we don't even know that they're happening. Okay? So the basic premise of our book and the research field that we are trying to represent to a broader audience is that we need to, in addition to legal, regulatory, policy, and other solutions, we need to think about embedding social values into our algorithms. And so I literally mean changing the code of our algorithms in order to incorporate social norms that we care about. Now, one of the interesting things, maybe the most interesting thing about this exercise is that, of course, if you're going to explain something to an algorithm, if you're going to encode a social norm into an algorithm, you have to be exceedingly precise in your definition of that social norm, right? You need to be able to write the code that implements it. And so even though we will be the first to acknowledge that there are centuries or maybe eons of scholars and thinkers of all variety who've thought about, fairness for way longer than we have, and privacy for way longer than we have, and other topics as well. Legal scholars, philosophers, economists, et cetera, that have thought about these issues have never had to think so precisely about them that they could be put into a computer program. And sometimes the very act of forcing yourself to think that precisely will expose flaws in your intuitions about topics like fairness and privacy that you wouldn't have uncovered if you were thinking in a looser, more macroscopic way. Okay, so I'm listing here several different social norms that are ones that there's a lot of discussion these days about, can we encode these, so can we give satisfying definitions of these different notions and then encode them in our algorithms. And you notice that they're in kind of increasing grayscale here as we go from top to bottom, and roughly that grayscale represents, in our view, how much is known scientifically about these topics at this moment. So we feel that, for instance, the study of data privacy and algorithms for enforcing data privacy is the most mature of these topics, and furthermore isn't the most mature but has kind of a central definition that we argue is the right definition, which is differential privacy, which I'll talk about in a minute. The study of fairness is off to a fast start. It's much, much more recent. But as we'll see, it's still more embryonic, and we already know that it's going to be messier. there won't be a definition, there won't be a differential privacy of fairness in the way that I'll describe. We already know that we are going to have to maintain multiple notions of fairness, and this is just the scientific reality. Similarly, we have things like accountability and interpretability, which we talk less about in the book, not because we think they're less important, but there's less to say scientifically of the type of science that we're interested in here. And then one might, of course, already put morality here, and I promise you there's a final bullet there, which is the singularity, but you can't see it because it's entirely in white. Okay, so what I want to do just in the first part of this talk is spend a little bit of time talking about privacy and fairness, which together with the introduction takes up about the first half of the book. And again, these are the areas where I think we're on the firmest ground, and give you a sample of what's known there and why this process of thinking hard about definitions can be quite revealing even in and of itself. Then I'll take one slide to kind of tell you about the second half of the book, which takes an interesting left turn, but a related left turn. And then what I want to do in the last part of the talk, maybe last third, maybe a little bit more if I'm lucky, is just tell you more about some scientific, some actual research going on in this area that we and others have been involved in trying to move fairness definitions from these very aggregate, coarse group definitions to ones that provide stronger guarantees to individuals in a population rather than just groups. Okay, so that's the game plan. And so let me just start off with privacy, okay? By the way, I won't call it out specifically as I go through this talk, but the influence of MSR is all over in this talk and all over in the book, so Differential Privacy was founded by Cynthia Dwork and her co-authors when she was at Microsoft. A lot of the fairness research that we implicitly discuss in the book and that influences our own research is done by MSR people, which has a fantastic fake group. But so let me start off by talking about why thinking hard about definitions is a valuable thing even before you get around to putting it into algorithms. So this quote at the top of the slide here is actually due to Cynthia Dwork. Anonymized data isn't, and the way to parse that is that either you haven't anonymized the data, and so it's not anonymized data, or you've anonymized it so much that it's not really data anymore, okay, and so it's not useful for anything. And so prior to differential privacy, or maybe even to this day, the prevailing formal definitions of privacy, including all those, in my view, unfortunately, that are in force in industry and practice today, are all based on notions of anonymization, or things like removing personally identifiable information, PII. And so the basic idea is you try to get some sense of privacy or some assurances of privacy by taking a data set and redacting certain columns entirely or coarsening others in the hope that by doing this, you can't re-identify any particular people in the data set. Okay, so in this toy example at the top, there's a database of medical records from a hospital, maybe it's the hospital of the University of Pennsylvania, and in the efforts to anonymize, it's been decided that names should be redacted entirely. Ages, rather than being given precisely, should be grouped by decades. Genders left alone. Zip code, last 2 digits are redacted, et cetera, et cetera. So some columns we've removed entirely, others we've coarsened, okay? And one notion that's popular in kind of the scientific literature on anonymity would say something like, okay, you should do these 2 operations, redaction and coarsening, until your database has the property that for any particular individual or line in that coarsened data set, there are many, many records that match it. So whereas before this redaction coarsening, maybe your medical record was unique in the sense that nobody else's attributes matched exactly yours. The goal here is to make lots of people match, and so then there's allegedly confusion about who's who. Okay, so for example, at the top, this is a too anonymous data set in the sense that for any particular entry in this table, there's at least one other matching entry. And so let's suppose, for the sake of argument, that you have a neighbor. And so because she's your neighbor, you know stuff about her that you couldn't get out of this redacted database. You know that her name is Rebecca, and you know that she's a 57-year-old woman, okay? So from this other source of data that you know about your neighbor, you can go look at this database and say okay, there's two possible records that match what I know about Rebecca, and they're the ones highlighted in red. And so now you have some uncertainty, right? The idea is now you're not sure which one belongs to Rebecca. I note that already you know that she's either HIV or has colitis, and she might consider your knowing the or of those a violation of her privacy already. And you might try to wish this away by saying, okay, no, in a real medical database, there'd be 10,000 records, and I might do enough of this that 100 records match Rebecca, and so now I'm really confused about what her diagnosis is. The real problem, of course, is triangulation, right, or linkage analysis, as it's sometimes called. So in this second database, which is maybe the database of Jefferson Hospital in Philadelphia, you might also know that Rebecca had been a patient there. Maybe you gave her a ride there one morning. And so in this database, this has been sufficiently anonymized that 3 records match Rebecca. And now, of course, from the join of these 2 databases, you uniquely know from the top and the bottom that she's HIV, okay? And, you can try to wish this away in various senses, but maybe the most damning thing that I could say about this entire category of definition is a statement in plain English, which is the problem with definitions like this is that they pretend like the data set in front of us is the only data set that exists in the world or that will ever exist in the world in perpetuity. And they don't anticipate other information I might know, like about my neighbor Rebecca, because she's my neighbor, or other publicly available information that all of us have offered about ourselves, thinking that it's innocuous, like our activity on Facebook or our social media posts, okay? And so we argue in the book that these types of definitions are fundamentally flawed, and one of the reasons that they're fundamentally flawed is that they're kind of ad hoc. They don't start off by saying, this is what privacy should mean, and now can we design algorithms that meet that definition of privacy? They sort of say oh, look, if you do this, then it sure seems like there's some guarantee of anonymity here. And I would offer a very crude metaphor, which is from cryptography. So those of you that know the history of cryptography, in my view, the history of cryptography up until the development of public key cryptography in the 70s, more or less had the form oh, well, if we scramble up the letters this way, it sure looks random. And it looks random until it doesn't look so random to somebody, until somebody cracks the code, and then it's all over. And the advent of public key cryptography in the 70s basically put the study of encryption and security more generally on kind of firm algorithmic footing, right? It basically gave a definition that said, this is the criterion that should be met. And then the question is, can you design algorithms that meet that? So continuing with this metaphor, we think that if things like anonymization are pre-public key cryptography data privacy, we think that sort of the corresponding landmark in privacy to public key cryptography is differential privacy. But before I talk about differential privacy, let me say okay, so I've pointed out one flawed type of definition for privacy. Let's step back for a second and say, well, what would be the strongest definition of privacy that we could possibly ask for, okay? And again, you can make this mathematical if you want to, and people have, but in plain English, one perhaps strongest definition of privacy I could give is I could say, look, it should be the case that any analysis that involves your private data, whether it's the release of a data set that's coarsened in some way, or the result of a computation that involved your data in that computation, or the release of statistics about a database in which your data was present, whatever it is, no harm should come to you as a result of that statistic analysis or computation, period, full stop, okay? So certainly that is a very strong definition of privacy. Nothing bad can ever happen to you from an analysis that involved your data. Okay, let me argue that this is asking too much. This is asking too much because if we insist on this, we basically won't be able to do anything with data, including many things that we'd very much like to be able to do. So suppose it is 1950, and I picked that year very particularly, and suppose you're a smoker. And if it's 1950, you're almost certainly a smoker because in 1950, pretty much everybody is a smoker. There's no health stigma associated with it. There's no social stigma associated with it. It's actually seen as fashionable and glamorous, okay? And suppose you were asked to participate in a medical study that asked for your medical record and your smoking habits, which was actually conducted in a famous study in England in the 1950s, sort of after the period I'm proposing that you were a smoker, and you go ahead and you say, sure, go ahead and use my medical record. And then as it did, this record, this medical study establishes a firm link between smoking and lung cancer, okay? So the fact that you were a smoker was public knowledge. You didn't hide it. Everybody that knows you knew that you were a smoker. Now, your medical record was used in the study, and now the world knows that smoking and lung cancer are linked. And now everybody's posterior belief about your having cancer goes up as a result of this study. And in particular, your insurer might raise your premiums because of this Bayesian update, so to speak, okay? So we could really say that actual harm came to you. Your data was used in this analysis. This analysis established this link between smoking and lung cancer. So harm has come to you as a result of this study. So therefore, under the definition of privacy that I proposed, you wouldn't be able to do this study. Okay, so clearly this is asking too much in the sense that we won't be able to do scientific research that's data-driven if we insist on this notion of privacy. And this brings us to the definition of differential privacy, which is a similar kind of definition, but weakened in an important way that sort of makes it practical while still providing very strong guarantees. And so the observation here is that in this story about the smoking and lung cancer, even though your medical record was used in that study, it's not like your medical record was the key piece of data that established the correlation between smoking and lung cancer. The correlation between smoking and lung cancer is what we might call a fact about the world that can be discovered from any sufficiently large data set. It wasn't that your data's inclusion was crucial. It was just that there's enough data, okay? So the definition of differential privacy sounds similar, but is weakened in an important way. It basically says that no harm should come to you as a result of an analysis involving your data that wasn't going to happen to you already if you hadn't included your data, okay? So you do a thought experiment in which you imagine an algorithm that's, let's say, getting many people's medical records as input, and you basically say privacy is preserved if for any particular individual in the input database, if we compare the result of the computation including all of the data and the result of the computation in which we have n-1 records with just your record removed, if the output is almost exactly the same, then we have differential privacy, okay? And if one looks at the definition of differential privacy, you'll see that, interestingly, it requires randomization because the notion of the output being nearly the same is a distributional notion. So on any given input, the algorithm induces a distribution over possible outputs, okay? And what can't change much when we include or don't include your data is that distribution in a technical sense that's quite standard, okay? And to demystify this a little bit, the way differential privacy works, the way you achieve differential privacy when you can achieve it is by adding randomization to computations. So if, for example, I want to publish in a differentially private way the average salary of all Microsoft employees, what I do is I do the traditional non-private computation in which I just take everybody's salaries, I average them together, and I output to numerical precision what the average salary is. I don't do that. I do the precise computation, and then I add, let's say, Gaussian noise with zero mean to that number that I get, okay? And it turns out by adding the right amount of noise, you get two desirable properties. You obey differential privacy for each individual salary in the input data set, but yet the output will still be quite useful. So to a first approximation, it's fair to say, in this specific example, if there are n employees of Microsoft and I add sort of order noise whose variance is on the order of 1 over square root of n, I will achieve this definition. Okay. Now, differential privacy, I think, was first defined in about 2005, and its theory underwent a great deal of development in the 10 years subsequently. When I first saw the definition of differential privacy, I'm a relatively recent, researcher in the topic. When I first saw it, I said, like, well, okay, that's a great definition of privacy. That's kind of the strongest definition you could provide while still hoping to do useful things with data. But I was worried that it's too strong, that the computations that we want to do in machine learning, for instance, wouldn't be able to be made differentially private. Subsequent work has happily shown me to have been wrong. So for example, pretty much every method, tool, or computation in statistics and machine learning, whether it's classical hypothesis testing methods or backpropagation for neural networks, none of them are differentially private. All of them have modifications that are differentially private and still give answers that are quite close to the non-private deterministic computations. So we know how to do machine learning in a differentially private way. And differential privacy has started to gradually creep into practice and products. So for instance, Apple was one of the first companies to field differential privacy in the iOS reporting of app usage statistics to the mothership in Cupertino. The big moonshot test for differential privacy is coming next year, when the US Census has decided that every single report or statistics it releases based on census data will be done under the constraint of differential privacy. And we talk about this a little bit in the book, but there's, even though the theory is well in hand and we know how to do all this stuff in principle, there's a lot of engineering considerations that have to be made, including about the trade-off between how much noise you add, which, of course, adding more noise gives you more privacy. There's a knob here, but you'll have less accurate answers.
Just to clarify, they're collecting detailed data, storing it.
They're collecting detailed data and storing it.
How they share
it. How they share it will be done under the constraint of differential privacy. And they have to, by law, collect that. They have. This is why they can't randomly sample. They actually need to literally canvass every single residence in the United States, or try to. Yeah.
So my question is related to your comment on the pragmatics of differential privacy and its variance. So the issue is that when you think about a very vanilla database system or a data system which serves up, you ask a question like a relational database system, it gives answers. It seems to me that what you are saying is that the notion of differential privacy has to be very tightly coupled with the task you are trying to do. So, and if that's the case, it creates a problem for the system developers, because let's say I want to claim my relational database system can support differential privacy. What is that supposed to really mean? Because the queries, after I get a result for a query, typical way people do it is they do a selection. And then, at some point there's a trade-off that you referred to between usability and the privacy.
Yeah, so if I understand your question correctly, I disagree with your characterization. So one subset of techniques in differential privacy is to take a database and to release a synthetic version of that database. So so it's not like differential privacy is only good if I have a database and I want to run back propagation on it. If I have a database and the object I want to share with people is a database, so that they can do SQL queries, the database has actual records in it that you can look at. It's rows and columns, it's a spreadsheet.
Right.
One technique in differential privacy is to start with an original database and to produce a version of it, okay, that will be a database and will basically preserve statistics of the original database. So there'll be some set of queries that you might have wanted to run on that original database. And what differential privacy will promise, you can't do this, by the way, in all cases, but when you can do this, the synthetic database will preserve, up to some error, all of the statistics in some class of statistics of the original database.
Clarifying question: you have to pre-specify the class of queries?
Okay, you're going down a great line here. If you can pre-specify that class, you can get away with adding less noise because you were able to commit to that before.
We can talk about
If it's adaptive, it's more complicated. And by the way, this ties in with the chapter that Eric was mentioning about the reproducibility crisis in the sciences, where you essentially are doing adaptive data analysis. You form a hypothesis, you gather some data, your hypothesis was wrong, but you saw something else that's interesting. So then you formulate a new and sort of a lot of the questions that you're asking are about, like, when can you do that? When is that okay? When can you do that without, like, creating entire fields of false science, right? Like food science, for example. Okay. Okay, so that's a little bit about privacy and about why thinking hard about definitions can sort of expose flaws in your thinking and lead you to a better definition. I want to sort of tell you, where we are in that agenda with fairness. Yeah.
Just to close the chapter on privacy, or is there any discussion about defining privacy in the terms of harm? It doesn't follow really.
So actually, if you dig into the definition so differential privacy there's multiple ways you can phrase the definition that are equivalent. But let me tell you the original formulation, which is exactly of the type that you're described. So the definition of epsilon differential privacy basically says the following. You have some private data. You're contemplating on whether to contribute it to some computation that will include lots of other people's data as well. Take whatever event it is, whatever outcome, now or in the future, it is that you're worried about, that you think constitutes harm. So this might be, the world learning about your medical condition. This might be your insurance premiums being raised. It might mean getting robocalls on your cell phone. Whatever harm it is you're worried about, you get to pick it, okay? The promise of differential privacy is that with respect to sort of the output distribution of a differentially private algorithm, consider the probability that this harm was going to come to you if you didn't allow your data to be used, and the probability that this harm will come to you if you allow your data to be used. Those two probabilities, whatever you're worried about, are within 1 plus or minus epsilon of each other.
Doesn't that then put the burden of proof into the other end? The definition of harm, then, it doesn't fall into the algorithm designer, it falls into the...
This is a universal quantifier. Anything that you're worried about, including things that you can't even articulate or think about yourself, are protected by this definition. Every single one of them. Okay, let me go on and talk about fairness. We already know that the study of fairness is unfortunately going to be messier, more complicated than privacy. One of the things that was interesting about writing this book is I'm like, okay, privacy is a social norm, fairness is a social norm. Discussions around fairness are much more divisive in society than discussions about privacy. At a high level, people have different attitudes about privacy for themselves. But in general, people are like, privacy is a good thing and we should all have it, okay? With fairness, you need to talk about fair to whom, for example, and you immediately go down paths that are very divisive and evoke strong emotions from people. So it's not just kind of messy in that social way. It's also, we know it's going to be messy technically. So we don't agree on the definitions. In fact, as a result of some very public controversies over fairness in criminal sentencing software, for example, researchers, a couple of different groups independently noted kind of what I might call like Arrow's impossibility theorems for fairness. So these are papers that say, okay, look, here are three different axiomatic properties that you'd like any definition of fairness to meet, right? And you look at these three properties and you say, yes, these are very weak properties. Any definition of fairness should certainly meet these three properties, and I'd like any definition of fairness to actually be stronger than this, okay? And then, of course, the punchline of the paper is, well, guess what? Here is a proof that you cannot achieve those three properties simultaneously, period, okay? So this means that not only will, as with privacy, there be trade-offs between, the social norm, privacy or unfairness, and predictive accuracy, there will actually be trade-offs there may be trade-offs between different notions of privacy. So it really might mean that if I want to build a predictive model that reduces racial discrimination, I literally have to do that at the cost of increased gender discrimination. Like this may be the reality, and there's just no squirreling around it. And stakeholders in society will have to make hard decisions about these kinds of things, right? People like us can articulate these trade-offs, but real stakeholders have to make their choices about them. But so I get a little bit ahead of myself. Let me just give a very brief tutorial for those who might have not seen these examples about why machine learning, even in its standard principled form, might result in discrimination of various kinds. And here's just, as I promised, the two latest media articles about apparent unfairness in statistical modeling. One from a paper from Science from a couple of weeks ago that established that a widely used health assessment tool used in many, many large US hospitals had systematic racial bias in it. And then the other one that you might have heard about, I don't think this one has been scientifically established, even though New York has already launched an investigation. You might have seen these media stories about the fact that Apple's new credit card to several couples who tweeted about it offered to the husband a credit limit that was 10 times that offered to the wife, even though they filed joint taxes and the wife had a higher credit rating, okay? So doesn't look good for Apple. Okay, but let me go back to basics here for a second and give you another kind of toy example along the lines of my medical databases. Suppose Aaron and I are asked to help the Penn admissions office build a predictive model for success in college based only on, let's say, high school GPA and SAT score. So here, each plus or minus here has an X value representing the GPA of some student, and the Y value has their SAT score. And let's suppose that these are students that were previously admitted to Penn. This is historical data. So we know for each one of these individuals whether they succeeded in college or not. And for success in college, pick any objectively quantifiable notion of success that we like. Maybe it's they graduated within 5 years with at least a 3.0 GPA. They donated $20 million back to Penn within 30 years of graduating. You pick your favorite, okay? As long as we can measure it, okay? And so there's a couple of things I want you to notice about this cloud of points. First of all, if you looked carefully at it, you'd seen that this population of past students, slightly less than half of them succeeded. There's a few more minuses than pluses here. Okay? In general, as you might expect, the pluses are sort of towards the upper right, higher SAT scores and GPA. And if I was asked to build a predictive model from this data, a simple threshold rule seems to do a pretty good job. If I sort of predict success for everybody above that blue line and not success for everybody below, I make some mistakes, right? There's some minuses above the line and some pluses below the line, but it does a pretty good job. Okay? Okay. Now suppose there's also a second population, subpopulation in our historical data, the red population. And I want you to notice a few things about the red population. First of all, they are a minority in the dictionary sense of that word, right? There are many fewer of them than the orange population. Notice that they're equally or even slightly better prepared for collegiate success. Half of them are plus, half of them are minus. But notice also, compared to the orange cloud, that the SAT scores, all these red points just seem like they're shifted down compared to the orange points. In particular, their SAT scores are lower, okay? And, one explanation for this might be that the orange demographic is wealthier and pays for SAT preparation courses and multiple retakes of the exam and reports only the highest. And the minority red population doesn't have the financial resources for that, so they just take the exam cold once and that's it, okay? Now, notice also that, if I build a predictive model for the red minority population, there's now a perfect classifier for separating plus from minus. But if I combine the two populations and I just say, look, the overall goal is to maximize predictive accuracy, minimize the number of false positives and false negatives, then basically I'm still going to pick the model that's determined by the orange majority, because you can see if I try to shift that line down to include the red pluses, I will pick up so many more false admits from the oranges that it won't be worth it. Okay? So this is one of several ways that just the usually sound principles of machine learning can result in a model that has systematic racial discrimination. Now, you might notice, like, well, look, suppose we just notice this thing about SAT scores. It's not that the red population is less successful in college. They just, for whatever reason, have lower SAT scores. I might propose a hybrid model in which I say, like, look, if they're an orange applicant, use the upper line, and if they're a red applicant, use the lower line, okay? And not only is this a more fair model, right now the false rejection rates between the two populations are much closer than they were before. Now I'm actually more accurate as well. So this is what I would call like a Pareto improvement. If my two criteria are fairness and accuracy, I've actually made both of them better. Unfortunately, many laws and regulations in the United States, in, for instance, areas like lending, explicitly forbid this type of model because this is a race-based model, right? I am looking at the race of the applicant, orange or red, first, and then it's like a decision tree. If they're orange, do this. If they're red, do that. And so this kind of points out how wrong-headed those rules and definitions are. This idea that by excluding race as a variable from your model, that you're going to protect a minority group. This simple example shows you that not only might you not be helping that minority group or protecting them, you might be actively enforcing damage on them by refusing to allow the model to look at this variable. Okay? Okay, now notice though that if I wanted to fix this problem algorithmically, there's kind of a straightforward path to doing so. So in particular, right, for any particular line like this one, I can write down two numbers. I can write down its overall error rate on the data, on the entire data set of the two populations combined. But another number I could write down is the sort of unfairness measure, right? So in this case, I might say that what constitutes harm is false rejection, rejecting somebody that would have succeeded in college by our definition. And this particular model here, right, has a false rejection rate on the orange population that's quite small. It's basically the fraction of pluses below that blue, orange pluses below that blue line. But its false rejection rate on the red population is 100%. Every one of the red pluses is rejected by this model, okay? But so now I could change my objective. I could basically say, instead of just like minimize the overall error, I could solve a constrained minimization problem, minimize the error subject to the constraint that the false rejection rate between the two populations is 0, or I could turn that knob and say the false positive rejection disparity has to be at most 1% or 5% or 10%. If I crank that knob all the way up to 100%, it's like I'm not asking for any fairness at all, okay? So this gives me a knob that lets me tune the trade-off between accuracy and fairness, or error and unfairness. And when you do that, you trace out what we would call like the efficient or Pareto frontier, right? You get a class of models corresponding to the different trade-offs you can make between these two unquantities. So on 3 real different data sets, I won't go into the detail, each red dot corresponds to like a different model. The x-axis is the error of that model. Okay, so lower is better. The y-axis is the false rejection disparity, or the unfairness of that model. So again, lower is better. We'd like to be at 0, 0. That's not happening on any of these curves. We can choose to go for the lowest possible error, ignoring fairness, and we'll get bad unfairness. We can choose to go for 0 disparity or unfairness and get the worst error, or we can get anything in between. Now, there are lots of models that are not on this line, right? They're above this line and to the right. you don't ever want to consider those models if these are your two criteria, because they're dominated, right? You could always move to a model on the efficient frontier and improve in one or possibly both of these measures. But one of the points we make in the book is that whatever social norm you decide to encode in your algorithm, whether it's privacy or fairness, it's going to come at a cost. At a minimum, it's going to come at a cost to predictive accuracy. And these curves are exactly quantifying what that trade-off looks like. And then it's, again, up to stakeholders, right? If this is sort of, false rejection disparity in admissions decisions, and this is accuracy of our predictions, admissions offices need to get used to looking at a plot like this and committing to a point on it and justifying that point. Yeah, question.
So I missed somewhere in your definition of fairness and the inclusion of race and criteria. Why just not conditioning on something like household income, which predicts race, but also identifies, majority factors where they can't retake the test either, right? If you're from a low-income group, but a majority group, you also can't retake the test. And presumably the same argument you gave applies to that group as well, that they would be skewed there essentially because it's not a good measure overall of how they perform over multiple tests.
I'm not quite sure I follow what the question is.
You proposed the argument that race should be included explicitly to fix some of these issues, but the underlying causal argument you gave was household income and access to resources.
Just to be clear, I'm not proposing that including race fixes anything. I'm proposing that insisting on excluding it might cause harm. They're not the same thing, right? So, another way of putting it, as we put it in the book, is that we think that good fairness definitions, and unfortunately or fortunately there are multiple competing good definitions of fairness I mentioned, but they should basically constrain the output of your predictions. They shouldn't constrain the inputs, right? You're fooling yourself if you think like, oh, by excluding race as a variable, that I'm somehow not racially biased, or that there aren't other proxies for race like zip code in my data set. So we're saying like, if your way of thinking is like, oh, I want to protect these different groups, and so I'm going to exclude we just think that that's false thinking, and that you're fooling yourself and can cause active damage. We don't say that like not doing those things guarantees like fairness, but we think that the right definitions of fairness basically say, your model should not exhibit this empirical behavior. That's a violation of fairness, and then it's up to an algorithm designer to figure out whether you can achieve that criterion or not, and at what cost.
So is it fair to say then what you're saying is that it should be included as part of the metric, but not as part of the optimization objective?
I don't have a prescription or recommendation for what inputs you use in building a model. I think fairness should be something that you define on the behavior of the model, and if you can achieve that definition, including or excluding certain variables, then fine. But we don't think the definition of fairness should be like, oh, a model is racially fair as long as it doesn't mention race as a variable. That's this is, I think, kind of roughly akin to anonymization definitions in privacy. Yeah.
So just to comment on that, I think that whether it's a proxy or not, the goal here is you still want to have enough inputs that you can discriminate appropriately. And the word discriminate I used intentionally here because the whole point of any classifier is to discriminate and put things in a right group.
I understand what you're saying. It's a confusing use of the word in the context of like discrimination of the social variety, but yeah.
And so, it's the comment is interesting, don't use race, but you still want to find the appropriate signal coming in, wherever it's from, or the data coming in, so that you can organize and get the right result coming in there. And I think that's...
Yeah, so in general, like if we...
That's not algorithmic,
sort of
that's data.
Computational and data resources set aside, if I didn't care about fairness, I want to add as many features to my model as possible just in case they might have some marginal predictive value, especially if I'm building something complicated like a deep neural network. But of course, when you do that, you also introduce more opportunities for things to go wrong of the variety that I described on the last slide. And this is why we and others argue that you need like a crisp definition about fairness that sort of is agnostic to what inputs the algorithm used, but constrains its actual behavior. Yeah.
So a few slides ago, you rejected the use of race as a choice of model, right? I use different model for different race. You reject as being not legal, right?
I mean, I didn't reject it as being not legal. The law rejected it as not
yes,
being legal.
it's not legal,
Yeah.
right? Why then it's legal to use race in the constraints? Why? Legally speaking, what's the difference? You are still using the race.
In what? In
the constraints. You're here in the
Constraints.
you're using the false positive per population per race as one of the constraints to build a model, right?
That's right. And so some of what I'm suggesting here, depending on the application area,
Right.
might violate current law.
Right.
So like our goal in this scientific study of fairness is not to adhere to current laws that we think make no sense.
Right, so-
We think eventually those laws will need to be rewritten.
Right, but my point is, why not just go back? If you argue we should use race as a factor to make a decision, why don't we just use race?
Okay, just to be clear, like in this toy example, allowing this two-part model will not necessarily solve all racial discrimination. I can give you a different data set in which even when I let you have a two-part model that uses race,
Right.
you still will have discrimination against one population or the other, and you need to explicitly decide to enforce
Right.
a fairness constraint in your optimization. Okay.
So basically, you reject this
Yeah.
approach.
So just
it's
because
so simple.
this example is constructed to sort of show you one thing that can break, the thing that fixes that in this particular example is not a general solution for that problem. Okay.
This seems almost an unwinnable race because you are going to get to a situation I can define a subpopulation ad hoc, like a predicate with a predicate, and say, hey, I want to be fair to them. And if I ad hoc start asking this, random collection of predicates that define the subpopulation, is there an
Okay.
algorithmic solution?
So if I get to it, this is exactly sort of some of the research that I would talk about. But Eric, advise me on how much time I actually have here. Huh? Okay. So we'll come to exactly this question shortly. Okay. So before I get to sort of the researchy part of the talk, let me just quickly tell you what happens in the rest of the book. And about midway through the book, we take, as I said, a wide left turn, but we think an interesting and relevant wide left turn. And let me kind of tell you what the basis of that left turn is. In all the examples I've given so far about violations of privacy or fairness and the like, and in many other of the social norms that I had listed on that kind of grayscale list at the beginning, like, interpretability, accountability, and the like, it really seems fair to a first approximation to think about individual citizens or consumers as the victims of algorithms. So in particular, maybe you get rejected for a loan by an algorithm. You don't even know that it was an algorithm that rejected you. You have no idea that it wasn't a human loan officer that looked carefully and thought about your application. So you might not even know this. And similarly, you might not know if your data was used to build such a model that made decisions about other people. We might be completely unaware of it. And as I said on the ethical hammer slide, right, we might not be aware that certain types of harms are being caused because nobody's sort of thought to look for them yet. Okay, and there's a lot of different ones that you can imagine. In other settings, there's an algorithm at play, but it's mediating the preferences of a large group of users who might have strategic or self-interested considerations. And it's not, I might even put it that the algorithm is mediating the preferences of a large population that might be competing. And it's not so easy, even though the algorithm or the collective of the algorithm and its users might exhibit undesirable social behavior, it's not so easy to entirely blame the algorithm. Okay, and this is where we kind of get into the realm of game theory and related topics. So let me give maybe what is the cleanest combination of something that can be precisely formulated mathematically and that people have everyday familiarity with, which is commuting or driving on the roadways, and the use of navigation apps like Waze and Google Maps, okay? So on the one hand, what could be better than Waze and Google Maps compared to when I grew up when, if you wanted, your goal was still the same. It's not to minimize the length of your the miles that you drive. It's to get from point A to B the fastest, and so traffic comes into consideration. Okay, and back in the 60s, that goal was still the same. I'd like to somehow figure out the fastest way of getting from my point A to my point B, but the means I had were like fold up maps in the glove compartment, which would literally just tell you the roadways available, and maybe like half-hourly traffic reports on just the major roadways that might be stale by the time that you're on that roadway. Okay, so what could be better than these apps, right? In response to what basically everybody else is doing right now, all of the other, all of the real-time traffic from everybody's GPS devices, these algorithms or apps compute my fastest route from my point A to point B. So in like game theory language, I might even say that they're basically helping me compute my best response to what every other driver is doing right now. Okay? So you can actually think about commuting or driving. It's a game, right? It's an incredibly complicated game. Like you can't write it down like Prisoner's Dilemma, but it is a game, right? Every driver on the road is a player. Every player has a payoff function or a cost function, which is the time it takes them to drive from point A to point B. These apps are basically computing your best response. They're computing your optimal route, given what everyone else is doing. And as such, they are literally essentially encouraging us all to play the competitive or Nash equilibrium of this very, very complicated game. Now, you might say, like, well, so what? How can that be a bad thing? If you've ever had any game theory, you know that just because something is in equilibrium doesn't mean that everyone or even anyone is happy with that outcome. And there are clean mathematical examples and some real-world evidence that show that, at Nash equilibrium, we might collectively be driving, let's say, as much as a third more, 33% more, than we might under some other solution, okay? Or which in economics would be called the maximum social welfare solution. So you can still imagine algorithmic solutions here. You could imagine a variant of ways that collects the same information from all of us. It takes real-time GPS information. It has a map of traffic right now. But instead of handing out to everybody their shortest driving time, it does some more sophisticated computation that tries to minimize our collective driving time, okay? So we talk about this. We talk about this not just in driving, but in things like, content curation, a la Facebook's news feed algorithm and many other settings as well. And we kind of go back and forth between talking about algorithms that could help these situations in which the system collectively is exhibiting suboptimal, behavior from a social standpoint. But the interesting thing is that, unlike fairness and privacy, you have to worry about the incentives. So if I propose some alternative to Google Maps and Waze that if we all adopted it would lower our collective driving time, I need to worry that individual people might say like, well, suckers, that's great that you're all doing that, but I'm going to open my way, I'm going to open Google Maps and I'm essentially going to defect as in Prisoner's Dilemma. And then, this would cause us all to possibly slide back towards the competitive equilibrium. And so we talk in this kind of gaming chapter about the algorithmic issues involved in making the algorithms better behave socially, but also kind of what the challenges are from an incentive or adoption standpoint. And then this other chapter that Eric mentioned, we kind of, follow the game theory chapter, the algorithmic game theory chapter, with a discussion of how these topics play out in data-driven scientific research, and how there is really, in some sense, a formal game going on there as well that's basically established by sort of the incentives of publishing and of publishers as well. And at a high level, this is getting back to the question you were making, if you take a field like machine learning, where we all share these benchmark data sets, and researchers want to publish in prestigious venues, and we're all kind of munging around on the same data and looking at each other's papers, so you're influencing and making me adapt my hypothesis. And the journals have the property that you can't publish negative results, right? If I go to the CFAR data set and I try some fancy new algorithm and I say, I tried this new method and it is not competitive with the state of the art, I promise you that paper will not get published at ICML or NeurIPS. And so you have this you have this machine that is essentially giving biased reports, where an uncountable number of experiments are collectively being run. There's a publication process that only tells us about the positive ones, right? So in the same way that, you always see this clickbait, eat this particular type of berry and it'll improve your health, and then 6 months later, that's not reproduced or it's falsified. We discuss with some seriousness the possibility that the machine learning community is driving itself in this direction, hopefully not that far yet. But we also talk about algorithmic solutions that interestingly include approaches involving differential privacy, like by kind of adding noise to data sets, or by changing sort of the information that we provide to competitors in these large ML competitions. We might actually sort of be able to balance between having a lot of experiments and research being done without having these problems of false discovery. And then we do have a last chapter on the things that we think are important, but on which there's less kind of firm scientific things to say, or not even kind of agreed upon definitions yet. And these include interpretability, accountability, and yes, we do even talk a little bit about the singularity at the end. Okay, so let me take, just for the aficionados in the audience, let me talk just a little bit about kind of more current research at a technical level. And one of the things that our group and others have been thinking about quite hard lately is definitions of fairness that provide stronger guarantees to the individual. So if you think about the types of fairness definitions I've alluded to so far, they are all group fairness definitions. So as a user of these definitions, here's what you have to specify. You first have to specify what group or groups it is you're worried about being harmed, that you therefore want to protect, okay? So you might be worried about, let's say, racial discrimination or gender discrimination, and then you need to say, well, what constitutes a harm, right? And so you might decide if it's college admissions, I'm worried about racial discrimination, and false rejection is the harm, right? Sort of somebody that would have succeeded that I rejected, and I might not think of a false positive as a harm. That's somebody who wasn't going to succeed but got in. They got lucky, but the other type of error I'm going to consider a harm, okay? And then what you basically do is you say, like, okay, this is the group I want to protect, this is what constitutes a harm, and what I want to do is sort of equalize the rate of harm across, the group I'm trying to protect and the majority, okay? And the pros of these definitions include the fact that they're relatively easy to implement, right? I can kind of adapt my objective function in the way that I describe and say, like, don't just minimize the error full stop, minimize the error subject to this false rejection disparity limit. So they have fairly strong theory and practical implementations. They provide no promises to individuals. So in particular, if in the toy example I gave, you were a member of the red minority that was falsely rejected from college, your consolation for the fact is the knowledge that I'm going to falsely reject qualified members of the orange population at an equal rate. So it's like I've committed an injustice to you, but you should feel better that I'm also committing that injustice to people different than you. At the other extreme, there is a literature on individual notions of fairness, okay? And these usually have kind of a metric-based quality, where you say similar individuals should be treated similarly. So, if I have two applicants that look very similar by some metric of similarity, then they should either both be admitted or both be rejected, but one shouldn't be admitted. And in general, these provide stronger guarantees at the individual level, but as you pointed out, right, if I go to the logical extreme of this, right, then I could sort of say, like, well, every particular person is a group unto themselves, and I want to, like, equalize the false rejection rate across all groups. So this is sort of an intractable definition because it doesn't allow me to make any kind of mistakes at all, right? As soon as if I falsely reject one person, I've got to falsely reject everybody, okay? So in general, the only, technical for the machine learning people in the audience, you kind of, to use these definitions, you generally need, what we call realizability. You need it to be the case that the ground truth that you're trying to predict can actually be represented in your model class more or less perfectly, which is essentially like a non-starter in the practice of machine learning, okay? So we've been spending a lot of time in the past several years trying to play around with definitions that somehow, don't go all the way to the rabbit hole of trying to provide like literally specific individual fairness guarantees, but are much more refined than these coarse group definitions. And there's sort of a lot of technical stuff on this slide, but let me skip ahead a little bit and give an example of the type of the definition that we have in mind here. So let's suppose that, let's say in college admissions or lending, we want to make sure that like the false rejection rates aren't just approximately equal across racial groups, but also across gender groups, and also perhaps across income levels and age groups and disability status and the like, okay? So I might say like, I'm going to add a lot of constraints now. I'm going to say minimize the error subject to the constraint that, across gender, the false rejection rate is the same. Across ages, it's the same. Across okay? So we know how to write that optimization problem down. It's not that different from these group definitions. It's just that now there's, a handful of groups instead of one, or attributes. Even if you do this, you still might end up with a model that badly discriminates against disabled Hispanic women over age 55 making less than $75,000 a year. Because I asked for fairness marginally in each one of those attributes, and I didn't mention anything about combinations. And I probably don't need to say it to this audience, but one of the things we say early and often in the book is that, especially when machine learning on complex models is involved, you should never expect machine learning to give you something for free that you didn't explicitly ask for, and you should never expect it to avoid a behavior you don't want that you didn't tell it explicitly to avoid, okay? You just should assume those things are going to happen if you didn't say them, okay? So this leads us to questions like, well, suppose I have a collection of attributes, and I'd like to not just promise fairness marginally, but on combinations of them or functions of them even more generally, okay? So this is sort of interpolating between group fairness and individual fairness. I'm not going to go all the way down to combinations of attributes that are so refined that they act as a fingerprint for each one of us individually, but I want to go closer to that than these group definitions. And you can write this down as a constrained optimization problem, right? It's not a problem to formulate it. It really is minimize the error subject to the constraint that for sort of all combinations of these attributes, you will have this approximate parity constraint with respect to whatever your notion of harm is, okay? Where things get interesting is the algorithmic problem now, because in the example I gave, for instance, if there are D of these attributes that I want to protect, there will be sort of exponential in D many combinations of them. And especially if D is large, I don't want to actually get this fairness by explicitly enumerating all the possibilities. So it turns out that there is a very nice algorithmic framework for solving these problems that when you can make it work gives you not just algorithms that are sort of efficient in the theoretical sense, but they are practical in the empirical sense as well. And I'm not going to go through these bullets, but I'm going to kind of tell you what the approach is. So the approach is to basically, write down this constrained optimization problem. And I'm going to say some things here that some people in the audience will understand and others won't. But you have this constrained optimization problem, but the problem is that there's the model space, first of all, might be very large. So the space of models that the learner is choosing from might be like neural networks. It's going to be, it's not going to be something you want to like exhaustively enumerate. So the learner has a very large space of models that they're searching over, as in vanilla machine learning. But now there's sort of an exponential or even infinite number of constraints on that model that come from the fairness considerations, okay? And so the first idea is to start with this constrained optimization problem and just sort of pass to its dual, like sort of classic convex or linear programming duality. And for those of you that are familiar with that theory, this basically lets you go from a constrained optimization problem to a two-player zero-sum game, okay? And in this two-player zero-sum game has an appealing interpretation. One player is the learner, and the learner's action space, if you like, in game theory terms, their pure strategy space, are like all the different models in their class, okay? All neural networks, for example. The other player I'm going to call, which is so the learner is the primal player, and the dual player is what I'm going to call suggestively the regulator. So the regulator basically is the way there to enforce the constraints. And so how does this game play out at a high level? At a high level, the learner, in round one, the learner just says, okay, I'm going to minimize the error on the data set, and they pick the neural network. And then the regulator, looks at that and says, okay, this neural network discriminates badly against disabled Hispanic women over age 55 making under $75,000 a year, fix it. And so this constraint gets added to like the Lagrangian of the learner, who now has to essentially balance between accuracy and fairness to disabled Hispanic women over age 55 making less than $75,000 a year. And so this back and forth goes, and of course, the worry about this back and forth is that it will maybe never converge or will converge only after an exponential or infinite number of steps. It turns out that if you can first of all figure out how to let the so-called best response of each of these players, if you can figure out how to reduce it to a standard non-fair like classification problem, which you often can, that's kind of technical step one of this agenda. And two, can figure out how to implement at least one of the two players as what's known as a no-regret learning algorithm, which I'm not going to bother trying to describe. But if you can accomplish those two steps, then this back and forth between the learner and the regulator will actually converge rapidly. And because part of the reduction involves an appeal to a standard learning algorithm, this gives an obvious way to implement this game in real algorithms, right? You basically, at a high level, you view something like backpropagation in neural networks as a subroutine. It doesn't know about fairness at all, but the players are kind of creating instances for training for that algorithm that encode the fairness constraints. And as long as one of the players you can implement in this no-regret fashion, this will provably converge. So basically, it turns out that this, by the way, this algorithmic framework is very interesting and might be reminiscent to some of you of GANs, by the way, where you again, set up a two-player game between a learner and a generator that's trying to fool the learner. And for those of you that are familiar with that literature, it wouldn't surprise me if sometime in the next couple of years, using something like this algorithmic framework, somebody actually kind of created a provably convergent version of GANs, where you actually would sort of say like, okay, here is the goal of the optimization. Here's a formal way of going from that to like LP duality, and here's an efficient algorithm that provably, because the way GANs are usually done in practice now, the setup is very same, but the execution of it is very ad hoc. You sort of run two players against each other, and it doesn't converge, and you sort of pick the point along the trajectory that looks the best. I'm going to skip the rest of this, but it turns out that this framework is good for several different types of definitions of fairness, in which one or both players might have a very large or exponential number of constraints, and this is what lets you get closer to these notions of individual fairness than these group fairness notions. And there's a lot of very interesting work going on in this general area by other groups as well. And let me stop there and take any Q&A that there's time for.
Thank you, Mike.
Thank you.
We have 10 minutes for questions.
Yeah.
I have a question about the last algorithm you showed.
Yeah.
So a potential practical issue with this is that the support from the data set, the size of the data set you had about a minority group is going to diminish exponentially as well as you are putting these constraints.
Good. Okay, so I skipped over the technical slide, but if you actually look at the constraints that we're enforcing, it incorporates that. So what I mean by that is suppose, for instance, you have sort of unlimited conjunctions of these marginal attributes that you want to enforce fairness on, and you want to get the combination. So basically, what we really put a constraint on is the amount of unfairness that group can suffer times its mass in the distribution. Okay, so what this means is that because I'm looking at the product of those things, if a group is a sizable fraction of the population, I've really got to make its unfairness equal to like the background rate. But if you get down to sort of vanishingly small subgroups, then I'm allowed to be more unfair to them. And there's no way around this in the definition for the reason that you say, right? If I really sort of ask that arbitrarily rare groups have to be protected, they might be so rare that even in a very large sample, they're not represented in my data set at all. There's not even a single member of them. And so you have to have, just for statistical estimation, convergence purposes, you have to sort of only make this promise to the groups that have some minimum mass in the population or the distribution, but then you can protect all of those, and there might be an exponential or infinite number of those already. It's a good question. Yeah, I think you were at the back next.
Thanks for the thought-provoking talk. My question is about differential privacy. Specifically, how do you convince companies to adopt differential privacy-based solutions in light of the following consideration? If you take a company like Facebook, right? So they ask you, to provide your age, a whole bunch of information about yourself, and you can refuse to do that, right? You can even fill those fields in with junk. But what Facebook can then do is ask somebody who are your friends, or just, some random people who might happen to know some information about you, asking them to maybe guess or provide or guess your age, for instance, okay? And then they can do anything they like with this information and then say, well, we're not actually using information coming from this person or exact information about this person. We're just using some guesses, right? And in this sense, they are vacuously differentially private, and yet, they still have a lot of information about you that can cause you harm that you did not provide. Yeah?
Yeah, so let me give a high-level answer. All of the algorithmic solutions, or maybe improvement is a more modest word, that I mentioned in this talk and that we discussed in the book, adoption of them by companies has to, if companies want to say that they're adopting these definitions and figure out ways of gaming them, the opportunities for that are rife, I think. So the companies either need to decide that they're really serious about this and they're not trying to fake it and kind of, say that they're doing differential privacy but having other means of circumventing it, or providing fairness in one place but, having it be not consequential to their bottom line, for instance. I think of those as kind of social problems or maybe regulatory problems, and I do think we're entering an era where regulatory forces on these companies are going to have much more teeth than they have in the past. You might have been making a more technical point about differential privacy, which I think if I follow what you're saying, an even better example of where differential privacy kind of doesn't promise you anything, even though you might think that it did. Some of you might have heard about these recent uses of genealogical gene sequencing websites to solve cold case murders, okay? So in particular, the Golden State Killer that was active in the 1980s, I think, was a serial murderer and rapist, and was never discovered, they didn't know he was. They had DNA from multiple sites of this individual, but the DNA didn't match any criminal genetic database. And so this was like 30, 40 years ago. But now have cropped these sites like 23andMe, where you can get your genes sequenced, and you can upload them to these sites that let you find your distant relatives and other dark secrets about your past that you never wanted to know. You've probably seen articles like this. And so a particular like a retired detective basically said, I'm going to unfreeze some of the Golden State Killer's DNA and uploaded it to one of these services, and they immediately found like several cousins of the Golden State Killer. And because these people are trying to find their relatives and are saying who they are and where they live, suddenly they knew, here are cousins of the Golden State Killers, and they live in this area. And this very quickly, like within a matter of weeks, led them to the Golden State Killer, who turned out to have been a former Sacramento police officer during the period that they were active. Okay? So even if you protected these genealogical databases with differential privacy, the Golden State Killer didn't contribute their DNA to these databases, yet these databases basically, revealed him. And the problem with DNA is that even though we might think of our DNA, our genetic sequences, as our private data, the problem is you share a lot of that data with your relatives. And if your relatives decide, for instance, to reveal that data, it compromises you in a way that differential privacy and no notion of privacy can possibly protect if we're going to allow data analysis of any kind at all. We have time for another one?
Yeah, Paul, and then.
So,
Sorry, two
on
more.
your notions of group and individual fairness, is there something that also looks at the two of them? So, in the case of group fairness, I'm worried that we create algorithms and we make them broadly available, and then we get into cases where, for the individual, it could be the Hispanic disabled female. Not only is she left out, but no matter how many times she tries, she never sees success because everybody is using the same algorithm. And whereas if you add just even a random probability of success, there's some probability that you succeed and that success adds more to it. Is there some sort of notion of amortized individual fairness?
Yeah, in fact, this slide, average individual fairness, I'm not sure if it's getting at the same idea you are, but it's basically saying like, well, if there's sort of multiple decisions that are going to be made about you across your lifetime, like what college you get into, whether you get a loan, what criminal sentence you receive, I could ask for a different type of individual fairness that doesn't say that on each one of those decisions you are treated fairly, but sort of that, your mistreatment across all of those decisions is sort of roughly the same as anyone else's. And so this sort of same algorithmic framework can be used for that kind of fairness. But I think there's another point that maybe you're getting at that this is not a solution to, which is that in an era of algorithmic decision making, so one of the things we say in the book is like, look, discrimination in decision making is not new to society because of algorithms, right? There were racist loan officers and are racist loan officers for, time immemorial. But at least like before algorithmic decision making, if you felt like you got rejected for racial reasons by one loan officer, you could always go and try others and hope that there would be a different decision. I think you're right that one thing that's special about algorithmic decision making is that it happens at scale. And so, for instance, I think I now believe that, conditioned on your being rejected by one bank for a loan, the chances that you'll be rejected by all of them are extremely high because they're all, using the same credit scoring agencies. They might, and even if they developed their own algorithm, right? Machine learning people like to think like, oh, their algorithms are unique, they're really proprietary, et cetera. But it's like really the data. If you have informative features about what you're trying to predict and enough data, then to a first approximation, we're going to arrive at similar models, even if we have different data sets and different details of our methodology. And I think that aspect of scale and uniformity of decision is a problem. And people, it's sort of I don't think I've said anything here about fixes for that problem, but you can imagine kind of obvious ones that include, for instance, the requirement of a certain amount of exploration, regardless of what model you're currently deploying.
Last quick question.
It's a rather technical question. So when you talked about the exponential number of constraints,
Yeah.
It's really exponential only in the number of attributes, right? Because at worst you have number of sample number of constraints, not because
No, so the number of constraints, if there's sort of D attributes that I want to protect and I want to protect all combinations of them, that would be exponential in D.
But it's not exponential in number of samples. And
No, but
it's at most
you
linear
need
number of
but in order to sort of, to say it kind of very technically, if I have an exponential number of constraints, the amount of data that I need to, make sure that my in-sample and out-of-sample fairness will be the same as only logarithmic in the number of constraints. So it's basically linear in D again. Yeah.
We should probably take any more about that
Yeah.
offline.
Yeah.
Thank you, everybody.